As we talk about functions as a mapping between two sets, such as the function f from a to b and the function g from b to c, we can also use function compositions as a way to map a directly to c, using some composition of g of f. We will look at this both graphically with diagrams and through equations. Function composition is essentially embedding one function inside of a second function to create a third function. So for instance, if we have the function f from the sets x to y, and the function g from y to z, then we can compose f inside of g as g of f of x, and it will map x to z. So composing two functions is a chaining process in which the output of the inner function becomes the input of the outer function. So for example, let's say we have f of x is equal to 2x. To diagram this function, we need to define some domain and codomain. So instead of using the whole set of integers, let's just say that a is the set that contains 1, 2, and 3, and b is the set that contains 2, 4, and 6, with the domain being a and the codomain being b. The diagram would look like this. Next, we can introduce some function g of x, so we have g of x equals x plus 3 as its rule, and it will map from b to the set c. So the codomain c, its set will be the set containing 5, 7, and 9. And finally, when we're diagramming g of f of x, we start with the domain a and the codomain c. So the domain of g of f of x will be the domain from the inner function f, and the codomain of g of f of x will be the codomain of the outer function g. We can also condense the diagram for f and g by putting them together with a, b, and c diagrams. And for our g of f of x, we don't need the b set diagram because it's mapping directly from a to c. Now to practice. Using the diagrams for f and for g, finish the diagram for g of f. So remember that we use the domain from the inner function and the codomain from the outer function. Also, we can see that in f, a maps to z. In g, z maps to 3. So in g of f, a will map to 3. And we can look at the same for b to x, x to 2, so b goes to 2. And c to y, y to 1, so c goes to 1. Let's also practice with the equation. Find g of f given that f of x is equal to 2x plus 1, and g of x is equal to x squared. We can solve this by starting off with g of f of x, and then writing g of 2x plus 1, then continuing to write it out. So this would be 2x plus 1 in parentheses squared, and you'd split it out and FOIL it and get the final version. So g of f of x would be 4x squared plus 4x plus 1. Just as we can find g of f using f and g, there are steps we can also take to find a missing g with f and g of f, or a missing f with g and g of f. With g of f, f is the inner function and g is the outer function. Let's say we have g and g of f, but not our f function. How do we figure out the values for f? In the diagram, we know that the domain of g of f and the domain of f must match. Also, we know that the domain of g and the codomain of f must match. We also know if there's a mapping from a to c, there must be some intermediate a to b to c that matches up. In g, we can see that 2 maps to 5, and in g of f, we can see that 1 maps to 5. So our mapping for f must be from 1 to 2. Likewise, in g, 4 maps to 7, and in g of f, 2 maps to 7, so we must conclude that 2 maps to 4 in f. And we have 6 to 9 in g, and 3 to 9 in g of f, So 3 to 6 would be in F. Now you practice. Fill out the unfinished diagram for F. So again, we can find the domain and codomain of F using information from G and G of F. And we can figure out the mappings for F by looking at G and G of F. In F, A maps to X, B maps to Z, and C maps to Y. How about with just the equations? How do we find f of x if we have, say for example, g of x is 3x, and g of f of x is 3x plus 3? First, we use a placeholder for f of x, so we can say f of x is equal to a. Then, we rewrite g of f of x, swapping out that f of x with a. With g of a, we can plug a into 3x in the g function. And with this, we can set the right-hand side of g of a equal to the right-hand side of g of f of x. So 3a is equal to 3x plus 3. Then we solve for a. And finally, once we have a equals something, we can replace the a with f of x again. So now you practice. Given g of x is x plus 2, and g of f of x is x plus 3, find f of x. Here are the steps you would take to solve it. Now let's find the outer function. Given that we have the inner function f and the composite function g of f, how do we figure out g? Again, we use the same domain and codomain rules to figure out what our domain and codomain for g is. So the codomain of f needs to be the domain of g, and the codomain of g of f should be the codomain of g. And we can write out each of the mappings to figure out where b is. So in f, 1 maps to 2. In g, we don't know where 2 maps to. And in g of f, 1 maps to 5. So this tells us that 2 must also map to 5. Again in f, 2 maps to 4. And in g of f, 2 maps to 7. So 4 must map to 7. And in f, 3 maps to 6. And in g of f, 3 maps to 9. So in g, 6 must map to 9. So with a little bit of investigation, we can find the domain and codomain and the mappings of a missing function. Now to practice. Fill out the diagram for g given f and g of f. This is what the diagram should look like. In g, x maps to 3, y maps to 1, and z maps to 2. Now, how do we find the missing outer function with the equations? Let's say we have f of x is 2x, and g of f of x is 6x. How do we find g? Again, we use a placeholder a, but instead of saying a is equal to f of x, which we already have f of x, we say a is equal to the right-hand side of f of x. Then we solve for x. Next, we know that g of f of x is 6x, and we're going to replace f of x with a, and x with a over 2. Then, replace a with x to get the final form of g. Now to practice. Given f of x equals x plus 1, and g of f of x equals x plus 3, find g of x. And here are the steps to complete it. With this section, it can be kind of hard to remember the steps to find the inner or the outer function that's missing, while it's pretty easy to find g of f or f of g. So practice all of these types of problems and make sure you know the steps.